Hi all, myself Ratnakaram Raju from the competitive.in, the only one platform at your service at any time to enhance your skills. Today we are going to discuss about heat and energy conservation. Then go to understand. Heat flow. If something warm is in contact with something cooler, the warm thing cools down as the cool thing gets a little warmer. This flow of energy called heat was until the 1800s envisioned as an invisible fluid called caloric as shown in the arrow. This wasn't such a crazy idea using fluid flow equations. Fourier correctly analyzed heat flow in the earth, inventing Fourier series to do it, and there existed at least one visible fluid, electricity. The idea was that temperature acted like a potential for the caloric fluid and it flowed downhill to lower T. Then go to next slide. What's wrong with the fluid heat theory? If you believe that things only rise in temperature when something fluid flows in, it's hard to account for the sudden rise in temperature of gas in an insulated, no heat flow possible container when it suddenly compressed by pushing down the piston. Basically, the caloric theory does fine in describing heat flow even in complicated shapes, but breakdown when work is done. Remember the one atom gas. Here is a piston. Okay, then go to another slide. The right approach, energy transfer. We have discussed work as energy transfer. The spring does work on the mass. The spring loses potential energy as the mass gains that amount of kinetic energy. Heat flow is another form of energy transfer as we know. We have seen that a hotter gas has more kinetic energy per molecule. Here is the extension of x where the spring force is given by F equal to minus kx, where F is the k is the spring constant, where m is the mass of the body. Then go to another slide. Units for heat. Since heat flowing from a hot body to a cooler body, one is just a transfer of energy. The natural unit is same as for energy, joule. The kilojoule, kg is often a convenient unit. An old unit still in wide use is the calorie. The heat needed to raise the temperature of 1 gram of water by 1 degree Celsius, the calories used in food labeling are accurately kilocalories. Finally, the BTU 1 lb of water by 1 Fahrenheit, 1 degree Fahrenheit. Then go to another slide. Joule heat things up. James Joule, an English brewer, measured the frictional heat generated by a measured amount of work. A falling weight drew paddles underwater in an insulated can. His result is called the mechanical equivalent of heat. 4.19 joule equal to 1 calorie. It is a direct question which is being asked in many small competitive exams. What is the value of 1 calorie? We need to just write or put the option with 4.19 joules. Then go down the slide. Internal energy of idle gas. We will consider first a monoatomic gas. Since it is idle, we are ignoring collisions or any kind of interactions. That is, we ignore any potential energy in the system. The only energy is the kinetic energy, and we know average molecule Ke is half mv square equal to 3 by 3 to kT. Important to notice here, this internal thermal energy per atom doesn't depend on the atom's masses. Then go to understand. Specific heats of solids and liquids. The specific heat C per unit mass of a material is defined as the amount of heat energy that must be supplied to raise the temperature of 1 kg by 1 degree Celsius. To raise the temperature of m kg by delta T takes sheet where Q equal to mcT. For almost all solids and liquids, C can be taken as constant over wide temperature ranges, but it changes dramatically when the substance meets or boils, as we'll soon discuss. Water has a very high specific heat, as we know, 4186 kilocalories kg degrees Celsius. Then go down the slide. Dulong and Petit Law. In 1820, these two professors in France discovered that the product atomic weight X specific heat was almost the same for many very different elements. We can now see this means the specific heat per atom is approximately the same, just as it is for the ideal gas. Elements with heavier atoms have lower specific heat per kg because there are fewer atoms in 1 kg. Let us take here sulfur. The C is 10 degrees Celsius, 710 degrees Celsius, mass of 32.1, where C into M equal to 22,800. For if we take mercury, 140 degrees Celsius C, joules per kilo kg degree Celsius, where it is M to 201, where it will multiply C into M, the value is 28,100. Then go to another slide. Here is a clicker question for you. I have 100 cc of mercury at 20 degrees Celsius in an insulated container. I pour it 100 ccs of water at 100 degrees Celsius. What is the final temperature after thermal equilibrium is established? Here is the options given. If you anyone know the answer, let me know in the chat box. Then go down the slide. Calorimetry is just thermal energy bookkeeping. As we know, two or more objects at different temperatures are brought into thermal contact and heat flows between themselves. Two objects A bat initially temperatures TA and TB, where TA is greater than TB, will reach an equilibrium temperature T given by A's heat loss, B's heat gain. It is given by TA minus T into CAMA equal to TA minus TB into CBMB. Then go to another slide. Latent heat. A large amount of heat has to be supplied to water at 100 degrees Celsius to turn it into steam at 100 degrees Celsius. 539 calories per gram as opposed to the mere 100 calories per gram to raise it from 0 degrees Celsius to 100 degrees Celsius. This does not change the RMS speed of the molecules. It all goes into potential energy, pulling the molecules away from each other against their attractive forces. Similarly, it takes 8 calories per gram to melt ice. This is why ice cubes remain in a drink quite a while. This is latent heat, as I said, must of course be included in calorimetry type bookkeeping. Then go to the slide. Evaporation. Recall that if water in a closed container initially filled with dry air, water molecules will leave the liquid until a liquid vapor equilibrium is established. The partial vapor pressure depending on temperature. There is a latent heat associated with this evaporation and it takes a little more energy to escape from water at 20 degrees Celsius than at 100 degrees Celsius. The cooler water is denser and the extracts a slightly more powerful attraction. As the vapor forms, the liquid cools, it's losing its fastest molecule. This is how sweating works. Then go to another slide. The first law of thermodynamics. A closed system has a total energy, internal energy, where it is given by E and T. This energy can be changed in two different ways. The system can do work W or have work done on it minus W. Heat Q can flow into the system or minus Q flow out. The first law is just total energy conversion where delta ENT equal to Q minus W. Change in internal energy is heat in minus work done. Then go to understand. States of an ideal gas. Suppose we have n moles of an ideal gas in equilibrium in a piston. The state of the gas can be defined by the giving the state variables pressure V, which are denoted by P and V. The gas state is a point in the PV plane. If heat is exchanged or work done, the gas state variables trace a path in the PV plane. If the gas moves along an isotherm PV equal to constant, its internal energy stays the same. The temperature and therefore internal energy is constant along an isotherm PV equal to constant. Then go to understand. The gas does some work. The gas pressure P meets the force from the gas on the piston of area A is PA. This means that if the piston moves up PADL equal to PdV. The work done by the gas in expanding isothermally along PV equal to nRT is given by W equal to integral from VA to VB PdV, which is given by integral from VA to VB nRT by V into dV, where it is given by nRT log of VA by VB by VA. I hope I discovered all the topics. If anyone have the doubts, let me know in the chat box. I will try to solve it in the next video. Thank you.